Okay, so I don't usually spend a lot of time on the live stream doing business stuff, but just because the final's coming up, I want to make sure we go through some stuff that's coming up. I know I've been talking about this a lot, but better safe than sorry. So I'm going to talk about it again. So here's the end of the semester deadlines. I just sent you all this information in Canvas, I believe, a few minutes ago. In case you haven't looked at that yet, just be aware there's a lot of deadlines coming up. So there's a homework check due tomorrow night on chapter 13. There's a lecture quiz on chapter 13 on Wednesday. Thursday is lab. Basically, I'm going to be on Zoom, but you don't have to be there if you want to practice at home, but you can just pop in with questions. Here is a list of the questions for chapter 14. This is what I consider the bare minimum, the ones in bold here. So 1, 2, 3, 4, 5, 6, about 7. So you could skip these 3 if you're running out of time to study, but we could do those Thursday in class after the quiz. We'll do some of these Thursday in class after the quiz and some today. Honor pledge. If you haven't already done so, do it. You get no points for doing it. You get -40 if you don't do it. It's got the rules. You got to do that. All right. So just straight up. If you haven't already scheduled your exam, there's not many times left. You better get on that right away. The written exam, Monday, May 10th, during class. Plan on being online the whole time. I think you should strongly consider joining me on Zoom. I'm not going to make you do it, right? But I could give you your own breakout room, and then you could just sit there, not be bothered by anybody in your own breakout room, taking the test. And if you have a question, it's really quick for me to help you, right? So just be aware that's there. This is something different. I'm going to probably set up separate turn-ins for the first half and the second half. I think that will make my grading faster. So, all right. After that, after the written portion, the class is not done. Okay. There's more work required. In particular, you need to do a post-test. This is all just credit for doing the points. This is easy points here, but get it done by that deadline. The oral exam, that's worth a lot of points. That's where you need to schedule it. If you haven't already scheduled that, look in the Canvas modules. Excuse me. And finally, required, I changed the due date on this. I want this done by next Friday. So just do that. That way I have time to grade and type in grades and get that stuff in the computer. So that's how this is going to go down the rest of the semester. Any questions about that? Well, I've got this up. Oh, here's where to schedule the oral exam if you didn't see that. Okay.
Do we have access for this document?
Yeah, I sent it in a Canvas announcement an hour ago or something.
All
So
right.
check it. Yeah, I got it all there just because Canvas doesn't do the best job of telling you when shit's due. I don't know why. It's like
All
seems
right.
like
Thank
something
you.
that should be so obvious, but they fail at everything. So yeah, got that. All
Yeah,
right.
thanks.
Yep. Okay. So with that said, the number one priority for you should probably be getting chapter 13 done. Yeah, that's why I do robjorsted.com, to be honest, because I hated all of them. Right. It's just like put my stuff up, never have to change it, and just leave it there and people can get it. And if I make a screw up, I fix it once and it's done. So I personally like my own. Yeah, anyways. All right. So here's the deal. Get chapter 13 done right away. That's your main push. Once that's done, we'll work on chapter 14 together. It's only 10 questions. We're going to do some of them today, some of them on Wednesday, probably 1 or 2 you got to do on your own. Thursday, study for the final. Hopefully you're already doing practice tests and stuff. And then, you should be fine on the final on Monday if you've been practicing. All right. And the oral exam will be pretty easy. It's just, talking about things conceptually, and you're not having to do the full calculations and telling me what procedures you would follow. So in that sense, it's like looking at the problem and saying, well, I should try this and this and this. And I'll throw a few curveballs at you, but you can work your way through it. Okay, so we are now up to chapter 14. If you want to have it open, page 127 is probably where you want to have the book open. Now I'm going to start with some whiteboard work. All right. And if we work hard, we could actually cover everything today. And then we'll just have time on Thursday or Wednesday for extra problems for practice and getting your homework done. So let's try and stay on it. If you can, try to be responsive when I ask questions, and it's okay to be wrong. Just take a guess and we'll just keep the flow going. All right. All right. And let me do speaker view. And let me get rid of this. All right. Oh, whoops. I need me up there. There we go. All right. So fluids. Very complex subject, extremely difficult. We are going to do a very small subset of it that is easy. So trying to really understand fluids is extremely difficult. Let's keep things simple. So we're going to start by understanding how pressure relates to force. So pressure and force are related. Then we're going to try to talk about pressure versus depth if there's no flow, no fluid flow. After that comes the buoyant force. So you know about the buoyant force if you've ever jumped in a swimming pool, right? The pool naturally helps hold you up. That's the buoyant force at work. We're going to discuss the equations and how to calculate it, etc. Finally, we're going to look at the Bernoulli equation, and that's basically fluid flow. We're going to do the simplest possible type of fluid. It's going to be laminar, meaning not turbulent, incompressible, meaning we don't, like, air is a compressible fluid, right? You can compress air. And so we're going to do the simpler case of, say, like water, which is pretty incompressible. So more on that at the end. Essentially, all this works out to conservation of energy for fluids. And as we've seen, kind of looking at chapter 13 verses 14, there's a pattern here. In chapter 13, we took all the tricks that we learned in chapters 9 through 11 or 9 through 12 and said, okay, let's do some force problems. Let's do some energy problems. And I even threw in an angular momentum problem. And so, cool. What are we doing in fluids? We're going to do some force problems and some energy problems. Seems pretty straightforward. What do we do when we get to physics 163? Some force problems and some energy problems. And then there's some kinematics sprinkled in here or there, plots and different stuff. But we're using the techniques of the first 10 chapters and just adding in one new type of force. Today, it'll be the buoyant force. Any questions about this before we start turning the crank? Okay, that's our goals. Now, let's start with pressure versus force. So pressure is defined as force over area. Now, technically, that's a magnitude. All right. So based on this, or anything you know, does anybody know any units for pressure? If I talk about pressure, do you know of any units of pressure?
Pascal.
Okay, there's a Pascal. A Pascal is the same thing as a Newton per meter squared, force per unit area. What are some other units, perhaps?
Millimeters per mercury.
Millimeters mercury. Torr is another one. What else?
PSI.
PSI, pounds per square inch. Notice pounds per square inch, that's a force per unit area. What else? Any chemists?
Marxist atmospheres.
Yeah, ATM. Oh, whoops, my bad. I missed it in the chat there. Sorry. Yep, totally. Oh, and good. Oh, old school. Somebody got the bar too. All right. So this is insane, isn't it? Look at how many different units there are. We're going to use this one because we use newtons and meters squared all the time. Now, if it helps, 1 ATM is equal to 1.013 times 10 to the fifth pascals, or newtons per meter squared. Yeah, we have PSI in there, Gonzalo. It's in there somewhere. Right there. Now, I just want to point out this number, look at it carefully. Do you agree it's approximately 10 to the fifth pascals? Or sometimes people will say 100 kilopascals. Right? Just ignore the 1.3. It's 10 to the fifth. All right. So if you're trying to get a rough estimate, these numbers are pretty good. 10 to the fifth pascals. What does this mean? Think about this. Now, this whiteboard, I don't know if you could tell here, it's approximately 1 meter squared in area. Not exactly, but it's a little less than a meter here, a little longer than a meter here. So let's assume that this whiteboard is 1 meter squared. What we're saying then is the weight of the air on top of this 1 meter squared area is 10 to the fifth newtons. If you go all the way to the top of the atmosphere, all of the air molecules in the column above this, all the way up to the universe, will be 10 to the fifth pascals, all the way up to the upper atmosphere. So the weight of air on top of this is 10 to the fifth pascals. That's what this number means. The force per unit area. If you have a 1 meter squared piece of paper, there's 10 to the fifth newtons down in air pressure. So far, so good. All right. Now, in this case, we could rearrange this a little bit. And I could see that if I want to talk about forces and I know pressure, just rearrange this. Anytime I have a force, I could rewrite it as a pressure times an area. And let me do something really quick here. Let's try to get a little less glare. All right. So very oftentimes in a physics class, what we do is if we know the pressure, we could convert that to a force, stick that in a free body diagram, and learn something. That's the basic idea of how we could use this equation right here. Now, let's take a look at, I'm gonna make up a problem really quick. Let me see here. Let's say we have a wall. Okay. Now, let's assume that we know that this side is 6 meters long and this is 3 meters tall, figure not to scale. Okay. So this might be the wall of a house or something. Actually, how long is a typical? I don't know. Maybe it's a little bit longer. Let's say it's, I'm going to cheat and say 10 meters. Okay. So let's say we have a wall that's 10 meters long by 3 meters tall. This would be the wall of your house. Now we know there's some forces acting on it. There's going to be a normal force up, an mg down, right? Now, in this case, let's say this is one, and let's say this is inside the house here, and this is outside the house. So we're looking at just one wall of a house. Sorry, you don't see the rest of the house. The rest of the house is there, but we're just not looking at it, okay? So we're inside the house. There we go. We're inside the house, just looking at this one wall. All right. Now, let's say some bad weather is arriving on the scene here. Sorry, there's a little glare. If you have bad weather, do you know what happens to atmospheric pressure? Goes up or down?
Down.
Down. Bad weather is associated with low pressure fronts. usually. Okay. So in this case, let's say this house is sealed up tight, the windows are closed, and it's at atmospheric pressure, which is, I'm going to cheat. We're not always going to do this, but let's say it's at atmospheric pressure of 10 to the 5th pascals. By the way, you see I'm drawing my P's as a capital P to distinguish it from lowercase p, which is momentum, and rho, which is density. So that's why I'm always doing this silly little serif there. Okay. P naught is atmospheric pressure. So usually P subscript 0 is the one reserved for standard atmospheric pressure of 1 atm. Got it. Let's say that there's bad weather out here. And this pressure is 0.9 times P0. It's a little bit lower. It's 10% lower than atmospheric pressure outside. If you had to guess, will there be a force on this wall associated with these atmospheric pressures? What do you think?
Yes.
Yes.
Yes. This blue one, which direction is that going to exert a force? Inside the house.
On the wall, trying to
Yes,
go out.
trying to go out. That pressure will be P naught times the area, right? Because this is a force, is pressure times area. That came from pressure equals force over area. So far, so good. There should be another force going this way. And it's not going to be as big. It's a little bit smaller. I'm going to say it this way, Gonzalo. There's a tendency for a force to exist from high pressure to low pressure. And so if you're thinking about the atmosphere, yeah, if there's a region with high pressure, it's probably got more molecules. There's going to be a force on it trying to push some of the dense area into some of the less dense area and reach equilibrium. Absolutely. Now, it's very complicated, but we can say this simple fact. If there's higher pressure inside than outside, there's a net force horizontally from high to low. There's a net. Now, if these are the only forces, what's going to happen to the wall?
It's going to start moving to the right.
Does that usually happen with a house?
Kinda makes it creak, doesn't it?
Well, yeah, but it's not going to translate. So there's probably some force over here that's got to take up the difference. Now, if you hear creaking, right, that's probably the ground holding this in, right? And so the ground is, and so now the top of the house is going to start leaning this way and creaking. Of course, the other side of the house is probably going to lean outwards the other way. So it's trying to explode. Hopefully the house does not explode. If you're in a tornado, how could you solve this problem and keep your house from exploding?
Equalize the pressure.
How do you equalize the pressures?
Open windows.
Open the windows. So if you open the windows, you'll have less of a pressure differential between the inside and the outside of the house. Hopefully it's almost nothing. And then your roof won't get ripped off. But yeah, it still happens. So yeah, maybe you don't see it. Maybe you're not home, whatever. But yeah, so it's, yeah, there was a tornado that went through my hometown when I was a kid. It was it's pretty scary. I'm from Illinois. So yeah, we were all huddled in the shower, right? The safest place in the house, because there's the most rigid construction there. Smallest rooms, most walls per unit floor area. All right. Anyways, if you wanted to, I just want to point something out here. We could actually draw this same FBD a slightly different way. This is another way you could draw it. What we could do is we could say there's a force associated with the pressure difference, delta P. So now in this case, the idea, oops, let me go up just a little bit there. The idea is this blue arrow and this red arrow could combine to form this one purple arrow. And the idea is the net force associated with the pressure difference. You're going to see this a lot. Now, if you've ever had to do any experiments in chemistry, you've probably had to use a pressure gauge. Gauges are reading pressure differences between the inside and the outside of a chamber. And so, for example, when you put a tire gauge on a tire and read the pressure, you're not reading the pressure. You're reading the pressure difference. Gauges record pressure differences. And so oftentimes, if you have a gauge, it's very convenient to use the gauge pressure to compute a net force from the pressure difference. That's not the net force on the entire object. That's just the net force from the two pressure differences, or from the pressure difference. So far, so good on that. Now, if you're curious about the numbers I chose, that's not that outrageous. A 10% drop in barometric pressure is typical. Hold on a sec. All right, there we go. So, and in fact, in question 14.4, I asked someone that was working with, I think they worked for the Weather Channel or something, but they were saying one time they had seen a drop as high as 15%. So a 15% drop in pressure is crazy. That's pretty insane. But you could look at 14.2 or 14.4, excuse me, later. All right. Now, I think that's about all there is to say. Any questions on this type of problem? There's forces. Don't forget about the force from each pressure, inside and outside. That relates to this thing called gauge pressure. All right. Now, so let's get up to our next topic. Okay, it's important that I mention this. It drives me a little batty sometimes, but I think it's important that we should at least say this. You'll see why later. Okay. The pressure at depth H is equal to pressure at the surface of a fluid plus density of the fluid times G times H. If I could draw a picture here, I lost my, hold on. Okay, so let's say we have some fluid here. Just a jug of water. All right. Typically, unless otherwise specified, we'd say the air pressure is 1 atm or 10 to the 5th pascals. Okay. What pressure do you think the water has at its surface, right here at this level? What pressure do you think this is? Right here.
10 pascals, the same.
The same, 10 to the 5th pascals. The idea is, if this pressure was lower than that, the water would squirt up into the air. If this pressure, if this pressure was lower than that, the water would be pushed downwards. If this pressure was higher than that, it would squirt up into the air. Well, in general, if I look at the ocean, we don't really see it moving up and down that much. Well, there's tides, blah, 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 but forget all that for now. So let's assume that the pressure at this surface equals P naught, unless told otherwise. Okay, we're going to assume, unless it's told otherwise, we have a normal day with normal atmospheric pressure, and we assume that the pressure at the top surface of our fluid is P naught. My question is this: How far below the surface do you need to go for the pressure to double? What should I do? How far below the surface do I need to go for the pressure to double?
Is it 2 times down, like, or all the way down to the bottom?
Well, what if this is 6,000 meters deep? If you go 6,000 meters down, there's a lot more pressure than double. So, yeah, my question is, how many meters down do I need to go? Rather than trying to do it in your head, maybe you could tell me what I should try and do with this equation. I want to find the depth at which pressure is twice as big as atmospheric.
Well, you can put, I guess you can do equation like 2 times the pressure equals P of surface.
Which
times
is atmospheric.
Plus the density of whatever.
Density GH.
Right, yeah.
Exactly. Let me see what's in the chat there. Yes, Jacob, yes. Same thing. So now take a look here. This P naught cancels that too. What do you get for H? P naught over rho G. Now let's do some numbers. This is approximately 10 to the 5th. Does anybody know the density of water in any units?
1
One what?
grams per centimeters cubed.
Yeah. Do you know how that is when you convert it to kilograms per meter cubed? I'll help out. It's 1,000. So we take 1 gram per centimeter cubed, convert it to kilograms and meters because Pascal uses newtons, which has a kilogram, and meters. So we get 10 to the 3rd. Give me a good number for G. That's approximately 10. 10. Thank you. Look at this. What's the depth? 10 to the 5th over 10 to the 3rd over 10. It's only 10 meters. Think about this. Think how high up the atmosphere goes. It takes all of that distance through all of that air to come up with 10 to the 5th newtons. Then you go through only 10 meters of water. You've figured out that's enough water to double the pressure. So if I went down here 10 meters, the pressure at this line would be 2 atmospheres, or twice 10 to the 5th pascals. Crazy. If I went down another 10 meters, what would the pressure then be? 30, or oops, yeah, sorry, 3 atmospheres, etc. So every 10 meters you go down, think about this now. Think about going to the Marianas Trench 6 miles down. Yowza. Think about the pressure. Crazy. All right. That's pressure versus depth. I want to be clear. This problem is a little bit different than almost every other one for this reason. Normally, for physicists, we talk about the lowest point in a problem being 0 and height going upwards. This is talking about depth H. So it's setting this to 0, and these are positive numbers as you go down. Very uncomfortable for me. I'm going to show you a way to do this later with the Bernoulli equation that looks more like what we did in chapter 8. All right. So as a caveat to this, let's say we have a dam. Okay, whoops. There we go. Now, let's say we have a dam holding back some water. We have a slab of concrete buried in the bedrock. Cool. Now, in this case, unless told otherwise, what do we assume the pressure at the surface is?
10 to the 5th pascals.
Okay, I'm just going to call it P0. As you go down, what should happen to the pressure?
Increase.
And it increases linearly. Now, because it's increasing linearly, there's a trick here. You could, if you wanted to learn about the force on the wall, on the dam wall, you could say, well, I know outside here is atmospheric. I know that this special one right here is the average pressure. And so the force on the dam associated with that pressure differential would be P average minus the atmospheric pressure times the area of the dam. So if you needed to figure out how thick this needs to be or how deep this needs to be so that it won't fall over, that's cool. Now, you could also see, where is the dam most likely to fail? Towards the bottom. So you've probably seen an actual dam usually looks more like this. Right? This makes sense. And then if you want to, we could even look at a top view of this dam. Okay, this is supposed to be a top view of the dam. Where it's arched. So in this case, if you haven't seen this before, you might look again at a picture of a dam on the internet or something, and you'll see that there's usually an arch here, right? And the idea is the arch can help oppose the tendency of this thing to collapse that way. So there's a massive force going this direction and only a tiny force going this way. You have atmospheric pressure on one side and many times atmospheric pressure on the other side. And so you need to make sure this dam doesn't collapse. So you arch it into the direction of the force, and that will help keep it from collapsing. That's some dam physics for you. All right. Thicker at the bottom, arched, you could make a dam. If you care, questions 8 and 9 kind of talk about that. An interesting side effect, if you look at problem 9, all right. Where is it? Come on. There it is. Say we have two dams. They're equally tall. First dam holds back water in a narrow canyon. The second dam holds back water in a canyon that opens up to a wide reservoir. Which one needs to be thicker?
Second dam?
Nope.
So first then.
Nope.
I guess they're the same.
Exactly, because it depends on depth. They're equally tall. And now we see one last piece. If we know that it takes the same amount of concrete for both of those scenarios, so it definitely makes sense to use the second dam. Think about it. If you have to do all this work to build a dam, don't build it in a canyon that's really narrow. Build it in something that's really narrow at one bottleneck, and then it gets extremely wide behind there. Because for the same amount of concrete, you could hold a lot more water. All right. So, and again, if they're equally tall, the water is of equal depth behind each dam. It doesn't matter how much water is back there. It just depends on the depth. Isn't that crazy? Because the force depends on the pressure difference times the area. The pressure difference depends only on the depth. Damn. Okay. Next. Let me see where I want to go next. I'm going to talk about another thing. Now, long before the internet was born, physicists have been doing YouTubes for hundreds of years. You could say physicists, chemists, whoever you want to. Scientists were the first people to really get into YouTube. By YouTube, I mean a tube shaped like the letter U. So there's a U-tube. It's literally a piece, you can think of it as a hose bent into the shape of a U. That is one type of U-tube. Now, let's say I throw some water in here. I pour it in and I let it kind of come to rest. Obviously, this side is going to this level. If I had poured water in here and let it come to rest, how tall is the water column on this side? Is it going to be higher than, less high, or equal to that height?
Equal to?
Yeah. This is the phrase water seeks its own level. Meaning if you take fluids, think about this. The weight of fluid in this column has to equal the weight of fluid in that column. Otherwise, let's say this was higher. It'd push down and squirt some of this up, and then they'd drag against the walls and eventually reach equilibrium. Again, when you first pour it in, it might slosh back and forth until it settles down. Okay, so far so good. Now, let's say I take some oil. Now, I'm going to pour some oil in here. And so let's say while I'm pouring it in, this settles down, and everywhere from here on up, I'm going to fill this up with oil. Okay, let's just say vegetable oil or something. So this side's water. That side's oil. If you had to guess, how will the oil level compare to this? Will it be higher, lower, or the same as? If you had to guess, based off anything you know about oil.
It should be lower.
Why do you think it should be lower?
It's more dense.
Okay, maybe you're using a different type of oil than me. Pour some oil on some water. Where does the oil usually go?
Never mind. It's less dense.
Top.
Yeah, so based off that, what does that make you say then? The same or different?
Opposite.
It's higher.
Yeah. So let's think. If oil is less dense, let's just say oil is 0.9 grams per centimeter cubed. Obviously, or maybe it's 0.7. The oil is going to float on top. And then the idea is, in this situation, it could be an equilibrium because the total weight on this side equals the total weight on that side. You could imagine splitting these in half. Right? And the idea is you could use this to figure out the density of different materials relative to water. You take a U-tube, you pour in some other material and see, hopefully it's not immiscible in water, but yeah, so in some cases this might not work, but this would be one way to see the density of oil. All right. Is everybody cool? You could measure the distances, calculate the weights, figure this out, have graduated cylinders. All right. If you're curious about this, give me a sec. Question 14.34 and a half shows you a picture of this on page 145. If you're into this YouTube physics, you could actually look at this. Ooh, zombie juice. Okay, so you could try and do this problem if you want. However, I don't think this was one of the ones I recommended doing, just so you know. But if this is into your, I mean, there's a lot of, this is a really, all these problems are interesting in this chapter, but you got to pick and choose your battles at this point. Just because this chapter is interesting doesn't mean you should spend all your time on it. You got a final coming, you know, a week from today. So just do the problems I said. In the summertime, if you find this stuff interesting, go back and do the extra ones. Okay. All right. Where were we? That's pressure versus depth. I think there's enough said on that. Remember that this pressure is force over area, and that's how I started talking about force. I know So in this case, the pressure down here at the bottom has to be the same. So I take the density of this fluid times the height of its column plus the density of water times the height of the water column. That should add up to the total pressure here. So if I could call this one atmospheric pressure. I could call this P1, the pressure at the bottom or the oil water interface. And then all the way down here, we could say this is pressure 2. And interestingly enough, the idea is we know the top here is at pressure 0 and this is at pressure 0. But then when you add up the two pressure versus depth equations, we should be able to get a relationship since they have the same pressure too. They're both at the same pressure down here. Otherwise, the fluid would go one way or the other. All right. Questions before we move on? Okay. Let's do a screen share here. Okay. Now I want to talk about buoyant force. All right. So this is tricky. The simplest way I know to describe it is this. The buoyant force on an object is equal to the weight of the fluid displaced. In equation form, it looks like this. Now, this can be very confusing. There's a bunch of words here. Let's start with an actual simulation here. Well, let's not simulate it. Here's some water, okay? Here's an object. It's floating in there. Now look carefully at the water level. If I could hold this perfectly still. Let me see if I can get this just right. Watch the water level carefully. I'm trying not to shake. Do you see it go up slightly? If I push it all the way under, you can see it goes up a lot. The idea is when I put an object in here, the volume level changes. That's the displacement I'm talking about. Here's another case. Tomato. Float, no float. What do you think?
No float.
Just barely doesn't float. In this case, you can see the volume level go up. All right. Now, my question here is, does this still have a buoyant force on it or not? Is it displacing fluid?
Yes.
Yes. So there's a buoyant force. Are there any other forces acting on the tomato right now?
Gravity.
Gravity. Anything else?
Would there be pressure or that besides the buoyant force, but just like normal?
The buoyant force is effectively going to replace that pressure calculation. More on that in just a second. So good thought. What else? The buoyant force is not enough to hold it up, right? It sinks. What's another force acting on the tomato?
Normal force of the cup.
Yes. So there's a big difference between something that floats. Hold on. Like this, something that floats and something that doesn't. In general, we'll see how this works. That's a 1 kilogram mass. I don't know if you could see that. 1 kilogram. Oh, what's up, Gonzalo?
Would friction be different underwater?
Yeah. All right. Now here, I don't know if you could see this. I'm going to try. I've got this cup of water here. I'm going to try and lower the Am I back? Okay, sorry about that. Pulled the cables out. So what I'm going to do is I want you to watch this scale. Oh my gosh. Zoom. All right. So now what I'm going to do is I'm going to lower this into the water. It's not in there yet, but there's the scale right about there. Let's see if we actually see this. It's going in the water now. It's very subtle. I don't know if you can see that. It did change ever so slightly. One more time. That's from the water, not from the bottom of the glass. All right. And so the idea here is as you go in the water, this is essentially like what we're seeing. When you displace more fluid, the buoyant force is not enough to hold it up, but it's trying. Okay. So the idea is if I'm trying to displace the fluid, or if I do displace the fluid, I'm going to create a buoyant force upwards. Let me dry this off real quick. So we see some challenging issues here. You should have page 135 open in front of you. You should have page 135 open in front of you, okay? Now, so what we saw here there's two distinct cases here, right? So the idea is here's something that's floating, here's something that's not floating. If I was going to do the FBD of these, and let me just put this a little closer, float, no float. That gives me a little bit more room if I do this and that. Okay, what does the FBD look like for this thing? What's one force that's acting on the floating object?
Buoyant force up.
A buoyant force up. What's the other one acting on this?
Mg down.
Mg. This one, on the other hand, what's going to be different in the FBD?
There's also be a normal force pointing up.
Yeah. Let me ask you something. Let's assume these two spheres are the same size. Which one should have the bigger buoyant force?
They're the same. Right?
No. This one is not fully submerged. You see the difference? So even though the objects are the same shape, this one is displacing less water because it's not fully submerged. This is one of the headaches of doing the buoyant force. So this object is more dense, it sinks all the way, and as a result, it actually has a larger buoyant force. It's just not large enough to support the larger mg. Oops. So the idea is we'd actually expect this buoyant force to be just a tiny bit larger because there's a tiny bit more volume under the surface. This is kind of the nuts. Now, this is where things get even trickier. We got to write these equations out. But any questions about this? All right. So now let me clue you into the rest of that page that I kind of glossed over. We have to be careful. In the buoyant force equation, we're going to try and write down FBDs and shove in this equation for the buoyant force. If we are to do that, we must be careful. The buoyant force depends on the density of the fluid, not the object. Volume displaced is, look how tricky this is. Normally, if the object is solid and fully submerged, volume displaced is equal to volume of the object. However, what if it's only partially submerged? It's some fraction of the volume of the object. And that is usually where the hard part comes in these problems every time, is you can't just stick in the volume of the object every time. The displaced volume could be less than. Here's where it gets even crazier. It could be more than the volume of the object. And now this at first might seem really strange. Let me get a quick example here. Oops. Whoops, come on. There we go. This is going to be the worst boat ever. This is just a paperclip holder. It's just a plastic bin, right? Just a plastic bin with some paper clips in it. Here's the ocean. Now, when I put this in here, I better not drink this water again because I don't know where this thing has been sitting. But the idea is it's going to float, right? Now, if I was trying to figure out the volume here, look at this carefully. Watch the displacement, if I could. You get this huge displacement there, right? But now the actual volume of plastic depends on the actual thickness here. The idea is if I wanted to get the volume of this object, the volume would literally be kind of like the area of this thing times its thickness. You know what I'm saying? So the volume of the object is this, whereas the volume displaced is everything this object could hold inside. Is that making any sense at all? Let me see here. So again, the volume of the object is the volume of material used to make a boat, whereas the volume displaced is how much water the entire boat, including the hollow air pocket inside, pushes fluid out of the way. All right. So even though this seems like it should be a cakewalk, it's not. I think we're about ready to do some problems here. Let me bring this back up. See if there's anything else I forgot about. Oh, previously, we would always talk about the weight as being mg, right? This is essentially a new way of writing mg, right? Because mass, well, let's try density equals mass of the object over volume of the object. So if you rearrange that, mass is equal to density times volume. So in a lot of problems, you're going to see me write mg in this way. It's a very standard trick in this chapter. Be careful. We're talking about the density of the object now, and we're talking about the volume of the object. And like I said, if it's a hollow shape, it's gnarly. Now be careful. The volume of the object is not changing whether it's submerged or not. Again, let me stress this with a visual. In this problem, right now, the volume of the object is like 4/3 pi r cubed because it's a sphere. Okay, approximately. Now, right now, the volume displaced is actually about half of that volume, right? So you'd say, oh, this is actually about 4/3 pi r squared, or 4/3 pi r cubed divided by 2. So that's the volume displaced, whereas the volume of the object is the entire thing. Now, I could do something weird and push this below the surface. And if I hold it below the surface, whoa, if I could, when I hold this below the surface, now the entire volume of the object is equal to the volume displaced. So, yeah. All right. Where did I want to go with this one? All right. Well, let's just look at these equations and how they pan out. Give me a sec. So what we would do here is for this floating one, I would say buoyant force equals mg. Then I would immediately change these to involve the densities. Density of the fluid times some volume displaced times g is equal to, let me color this in red, density of the object times volume of the object times g. We see the g's cancel out. And then I get, in this case, a relationship between these different objects. For example, in this case, maybe I want to figure out the density of the fluid that I'm using. I could solve this for density of the fluid and relate it to the density of the object in this case. Or let's say I want to find the volume displaced. Let's do that in this case. That's going to be the volume of the object times density of the object over density of the fluid. Whoops. Now let's think about this. In this case, we're talking about an object that was floating. What should be true about the density of the floating object compared to the density of water? More or less or the same? Less. So here I expect the volume of the fluid is, what did I say? Greater than the volume of the object. I flipped it. Sorry about that. So in this case, the volume of the object is less than that. So if we look at this number right here should be less than 1, right? And this makes sense. A floating object, the displaced volume is slightly less than the object. So far, so good. Now, over here, the difference on this side, when it's fully submerged, right? That's this case. Great. I'll scoot it up now. In this case, if the object's fully submerged, this is going to be density of the fluid times volume displaced times g plus the normal force is equal to mg. Well, in this particular case, density of the fluid is fine. This happens to be volume of the entire object in this special case. In the last problem, we couldn't do that trick because the displaced volume and the volume of the object itself is not the same. Now, these are the two main types of problems you could imagine with a buoyant force. Either something's floating that's not completely submerged, or it's on the bottom. And then what else could you do? You could attach another force to it. Like, for example, I was pushing my fingers down. I could ask a question on the test. How much force did I have to use to push that red plastic ball below the surface? Well, that would be very similar to what we did here, except you'd stick in another force from my hand, and the equation would look a lot like this. 3 terms, and you solve for one of them. Or I could say, let's say there's a string holding this up, right? Give me a sec. That's this case, right? There's a scale holding up this. And when I put it into the water, how much force does the scale read? Well, you've got the buoyant force up, mg down, and the scale reading up. So the idea is you could imagine doing a problem where there's 3 forces or something and do a calculation and solve for some parameter. I could ask you to solve for the radius of the ball. I could give you everything except the radius of the ball, and notice the radius of the ball would appear in the volume of the object. I'm going to pause here. Gonzalo, you had your hand up a while back. Did I address your question or not? Sorry for the long delay.
Yeah, you did. Thank you.
All right, cool. So, other questions? Anybody? All right. Let me show you something else here. Let's go into, let's do this. Oops. Jesse was talking about pressures. Now, I want to be careful. This is not my favorite way of explaining this, but I think you can see where this comes from. Jesse was saying something about, oh, forces, pressure, blah, blah, blah. Yeah. Take a look at this one. As you go deeper in the fluid, we expect the pressure to increase in size, right? Now, just below here, it should be the same size as those arrows on the side. I'm trying to draw these approximately to scale, but who knows if they are. What do you notice about the left and right arrows here?
They're the same size?
Yeah, so they're going to cancel out, right? What do you notice about the up-down arrows?
The bottom ones are larger, so it's going to push up.
There's the buoyant force, right? So in a sense, if you could work out the buoyant force for this case based purely on pressure versus depth. So far, so good. Basically, Jesse, this is replacing the delta P force. Are you good with that, Jess?
Yes.
All right. Now, why I don't like this is on the next page. Imagine you have objects that are sitting on the bottom of a pool. Most of you, whoops. Okay. Most of you would have no trouble saying, there's a little gap here. I could see the fluid getting in down there. So I could tell that there's going to be a buoyant force up. However, what about this case down here? Most of you would say, I don't see any fluid under there. If there's no fluid under there, there's no pressure upwards. I only have pressure downwards. This doesn't make sense. This is where the last problem is bad. Okay. The idea is if you put a block in here, the water level goes up. Let me clear these. I'm getting too many drawings. Initially, let's say the water level was right here. When you put the block in there, you displaced this water upwards. So there's some amount of displacement right here. I'll call that V displacement. If you do this, there's a force upwards on this, even though you might not understand, wait, there's no water getting under here. That's fine. Now we could debate whether capillary action would matter or not, or it's so complex. I don't want to talk about it. Just trust me when I say, if you have a block that's sitting on the bottom of a pool, it's got a normal force upwards and a buoyant force, just like the sphere does. And it has to do with this displaced fluid. So rather than thinking about forces, oops, that's an mg, right? This one's got an mg down. This one's got a buoyant force up plus a normal force up. Regardless of the shape, if it displaces fluid, you get a buoyant force. Try not to go crazy thinking about this and losing your mind. All right. So let me just leave it like that. All right. Questions on that one? Just trust me that a block at the bottom of pool experiences a normal force up. If you didn't believe me, you'd put a scale on there and weigh it. You'd see that it still has yeah. Okay. All right. I would like to take a short break and then come back and talk about fluids in motion. All right. And so my goal is to finish up this lecture today so that we could just do extra problems on Thursday and just be studying. I will say something really quick here. Let me show you this one. I want to finish up the buoyant force stuff now. This is a great problem. I think this is one of the ones I told you to do. It's how you could figure out the fractions. And here's where I'm talking about this fraction of submerged fluid. Here's hydrostatic weighing. So you could weigh something in and out of water. And from that, you could figure out its density. For example, this is used to figure out a person's body fat. So maybe you've seen that. Here's a weird one. You can make a boat out of concrete. If you are curious, Google SS Palo Alto. It's an old concrete boat sitting out there in the ocean that's not usable anymore. There's also, if you go to Cal Poly, there's the concrete canoe competition put on by civil engineers. So if you're a civil engineer, you should check out this problem. Look at this density. That's less than aluminum. Isn't that crazy? Anyways, and here's a fun one. This is one of the ones I said you definitely have to do. Okay, I think you can learn a lot from this problem because it's forcing you to deal with hollow object. And so you're going to have to think about the volumes. It's got densities. It's got a spring. So this has got a lot of challenging work. It says, what if it's stretched? What if it's compressed? And then similarly, 14.42. What page is that? Give me a sec. Oh yeah, got it. Let me just show you a couple others here. 144. Here's one where there's a normal force at an angle, right? You can see that's a good one. I think that's one of the ones I told you to do. There's another YouTube. There's a fun one. The scale, what's going to happen to it. And here's one with a hemispherical bowl. So if you could do all of those, you could handle any buoyant force question I throw at you. I sure hope it's not as hard as 42.5 or 40.20.5, but it could be as hard as some parts of that. All right. Let's call that good for right now. Let's take a short break, 5 minutes, come back and try and bang out the fluids in motion. All right. 5 minutes. Almost ready to get back into it here. All right. It's interesting. In person, there's so much more I like to go into in this chapter. It's one of my favorites. It's probably the chapter I struggled with the most in writing because it's very difficult to be accurate and not accidentally oversimplify something. It's a really cool chapter. There's so many interesting applications. Hydraulic press. You could talk about Flettner rotors and weird stuff and the Magnus effect. And a Flettner rotor is a very unusual sail. It's basically a large spinning cylinder, and you put it on top of a boat and you put a DC motor on it or something and have it spin, and you could actually increase the speed of a boat. It works. It's a very, yeah. Anyways, there's all kinds of weird applications of this stuff. Poisson, interesting stuff. However, we need to keep ourselves, restrict ourselves to a simplified set of materials. If you're really passionate about this stuff, the only way to really know what you're doing is to take a serious fluids course. Some engineers will have to. Fluids and thermodynamics are some of the hardest courses engineers have to take. They're just complicated. That's it. And you pretty much have to code problems to understand it. That said, we're going to keep it easy. All right. So that said, I want to go up to page 141. I'm going to start with the screen share. So again, I know I'm going quickly, but Wednesday after the quiz, or even Thursday in lab, we can do more worked problems. So I know I kind of rushed through Buoyant Force, but you have the guts there. All right. Now I'm going to talk about fluid flowing. And maybe I should have said this at the beginning. We're going to focus on the simplest possible fluids. They are going to be non-viscous. So we're going to ignore drag. They're going to be incompressible. So for us, that's going to mean constant density. And I think I showed you a video last time of the glass hammer filled with water, right? And we saw that the glass hammer was made incompressible by filling it with water that is very incompressible. Now, to be clear, you could compress it if you apply enough force, but we're saying it's basically, this is a fancy way of saying constant density. This is only approximately true. Over thousands of meters, sure, even water could compress. Finally, we're going to restrict ourselves to laminar flow. Laminar, think layers, like layers of a cake, or as you could see in this picture, layers of flow. See how there's different layers of flow. There's no turbulence. There's no eddies. We're not seeing stuff that looks like this, right? There's no vortices, right? We don't have this kind of stuff going on. So we're talking about laminar flow where all of the fluid is flowing in layers. Usually this is very slow fluid flow. Now, if there's turbulence and other things, take a more complicated class. All right. Now, some parameters that we're going to talk about. The density of the fluid, that's easy enough. Cross-sectional area, right? Fluid flow through a pipe. I'll show you an example in a second. Now, we've got this volume flow rate. Volume flow rate, I should have written this, you should add this in. It's equal to the area times the speed. The volume flow rate is not the same thing as the speed. It relates to it. The volume flow rate is how many meters, whoops, wrong color. How many meters cubed, that's volume, per second. And I think if you look at the units of area times V, you'll agree the units of that are all equal. So far, so good, I hope. So the speed is how fast one water molecule is moving. Rate is the volume per second. Next, pressure. Whoops, let me use a different color here. Pressure. When a physicist says the word pressure, we usually mean static pressure. And I exclusively mean that. So when you hear me say pressure, I mean the letter P, that means static pressure. You could think of this as being the pressure exerted perpendicular to the fluid flow. Right? Now, there is some in the path of fluid flow, but just for now, let's call static pressure like the pressure that is perpendicular to fluid flow. Okay? Now, there's also a thing called dynamic pressure, letter Q. Notice that kind of looks like kinetic energy. Do you see that? In fact, it is kinetic energy per unit volume, right? If you take M and divide it by volume, you get density. Now, that is the pressure going in the direction of the fluid flow, where the molecules are moving. So this is how I like to think about it. The pressure is pointing in every direction, whereas the dynamic pressure is the one special component of the pressure that's pointed in the direction of the fluid flow. Now, there's this thing called stagnation pressure. If you add these two together, that's the total pressure required to stop the moving flow. So if I wanted to stop this flow, like if I wanted it to smash into a wall, the stagnation pressure is that. To be honest, we aren't going to use a lot of these terms, but I just wanted to be clear. Pressure is a lot more complicated than what you see in your physics books. And I discovered early on when I was teaching this, students get really freaking confused by the fact that pressure is not the same thing as dynamic pressure. Okay. We're going to do a visual in just a second, I promise. The two main equations that we need to do are these two equations. This one says rate in equals rate out. If you have a pipe and fluid is flowing in, the rate at which fluid comes in must equal the rate at which fluid goes out. If this wasn't true, you'd either have a leak or you're going to have an explosion or some problem. Second, conservation of energy. We did forces, buoyant force already. Now let's talk about conservation of energy. You might not see this right away, but I'm going to write this another way. Let me just do this on the board. Okay. Let's say I have kinetic energy plus U plus work non-conservative or external equals kinetic final plus U final. And then rather than call them initial and finals, I'm going to be a little crazy. I'm going to be a little spunky. I'm going to use ones and twos. Whoa, I'm crazy now. All right. Ones and twos. So now in this case, this is a 1/2 mv1 squared plus mg height 1 I'll just call that W. I'm lazy. Okay. So far, so good, right? Just conservation of energy, nothing fancy. But wait a minute. Does anybody know any mathematical definitions for work? What was the definition of work? How do we do work in chapter 7?
Force times distance.
All right, I'll give it to you. Force times distance. And obviously there's a dot product, but let's be lazy. Okay. Does anybody see pressure?
So force times area, but or wait, is that right?
Pressure times area.
Okay.
And obviously the change in pressure times area is the net force, right?
Right. So you okay.
You take this crap, plug it in there. This side's going to have a pressure 1 times volume. This side's going to have a pressure 2 times volume. The pressure is the work. All right. So in this case, this is the change in pressure times the volume. Area times the distance would be the cross-sectional area times the distance traveled through the pipe. Now, we should actually be integrating and do all that, but it works out the same. All right. The fact remains, if I take this equation and divide everything by the volume, all the masses turn into densities. This particular one drops out and we just get pressure. Bernoulli's equation is essentially conservation of energy. Watch out, world. One thing we definitely have to look out for. In an energy equation, what does H mean?
Height above the reference level?
Height, not depth. So remember that pressure versus depth from earlier? We set 0 at the top and went downwards positive. Never do that again. You can now derive pressure versus depth using this equation. If the fluid's not moving, set this to 0 and you get back the pressure versus depth equation, except it's pressure versus height, which height makes sense to me as a physicist because usually we say set the reference level at the bottom of the problem. Whoops, I just threw a marker on the ground. All right. Let's take a look at a simulation. Okay, there's some fluid flow. This is considered to be laminar flow. When I run this thing, I see these fluid flowing. Or if I put these dots in here, notice the dots never cross over each other. They flow in a straight line. They're chasing out streamlines. Now, in this case, I'm going to run this thing again, but put friction on here. Normally, we ignore viscosity. Okay, if I do include viscosity, look at this. The points at the edge of the tube drag along the wall and get slowed down. We are not going to deal with that. That's too hard for us. Okay, we're going to start with a simple assumption that there's no friction at all, even though that's complete nonsense. Now, in this case, what is this parameter up here? What's the symbol for that?
R.
R. And do you agree we could somehow convert that to meters cubed per second? Liters is a unit of volume. Meters cubed is a unit of volume. Google it. You could figure it out. All right. So far, so good. Speed. So what we're saying here is, look at this. Anywhere in this pipe right now, the speed of these particles is the same. The pressure. Notice there's a small difference between the top of the pipe and the bottom. Why is that?
The depth?
Yeah, you're going up. Okay, so this seems to be reasonable. What's going to happen if I constrict the pipe in the middle? The flow rate has to be the same. What should happen to the speed?
It's going to speed up.
Much faster. Think about it. If you put your thumb over the end of a garden hose, the water squirts out faster. You still get the same amount of water, You still have the same R, you still have the same meters cubed per second, but the speed goes up. What should happen to the pressure?
It increases.
Interesting. What do you think I'm going to say? It goes down. This is where students get lost. They're like, wait, it speeds up. Shouldn't the pressure go up? Remember, Q goes up because that's the dynamic pressure. When I say pressure, I don't mean dynamic pressure. So the dynamic pressure is definitely larger there. However, pressure, which is static, actually goes down. Think about it. Let's look at this equation. Let me rewrite it. Here's our equation. We know pressure 1 plus 1/2 rho V1 squared plus, what's the other term? Rho G H1 equals, I'm just going to write these in reverse order. For fun. In this case, here's our equation. Pressure, dynamic pressure, a depth term or height term, however you want to think about it, gravitational term. So this is pressure in all directions, including perpendicular to the fluid flow, plus this one. All right. Now in this example, if we just look right on the midline here, so if I only go straight across in the middle, is the height changing? If I compare this point right here in the middle to this point right here in the middle, does the height change?
Yes.
No.
No, it doesn't, right? Because we're looking at the middle of the pipe in each case, the center of mass of it, right? So be careful there. Now, if we were being very delicate, I've tried to go exactly at the middle. Okay, Jess? So do you agree these two terms should drop out? So look, if this speed goes up, doesn't something else have to go down? That's the idea. And here's the issue. Pressure drops, so you have less force every direction. However, you have more speed, so you have more dynamic pressure in the direction the fluid flow is going. So I don't care how many times I tell you the pressure drops, you're not going to drink from a fire hose because of the dynamic pressure. Unless you're really into UHF. Weird Al Yankovic's movie from the way says, okay, kids, who's ready to drink from the fire hose? Side note, Weird Al is a Cal Poly alum, right? Did you know that? Anyways. All right. You guys probably know all this stuff. Okay, great. So here's the idea in general. What we could do, well, so now look over here. When I get over here, it's about 120. It's about 120. Over here, the speed is 1.6. What should be the speed when I get all the way over to the other side?
1.6.
About 1.6. So now what should happen if I lower this end of the pipe?
Would the depth change?
Okay, so what will that do to the numbers?
It shouldn't increase.
Increase which?
Increase the speed, lower the pressure.
Let's take a look. It's my attempt. And let's do this. It didn't lower the speed, did it? Why is that?
Because it's the same depth, it's just lower in the ground.
Fluid in has to equal fluid out. The rates have to be the same. The meters cubed per second on this side has to equal the other side, right? Otherwise, the pipe would explode or be leaking. So I need the same number of meters cubed on each side per second. That's one fact. Well, that's equal to area 2 times V2. Over here, that's equal to area 1 times V1. Well, if the pipes have the same area, they must have the same speed. Otherwise, fluid is leaking or there's an explosion and we're in trouble. As a result, all of the change is transmitted into pressure change. 120, 130. Again, this is not in violation of the equation. What we saw here is we're doing a different scenario now. In this situation, we see we could use the continuity equation in conjunction with the Bernoulli equation to learn something. We know if area 1 equals area 2, the only way that's possible, if there's no explosion or leaks, is to say V1 equals V2. If V1 equals V2, these two cancel out, and then the change in height correlates to a change in pressure. If H goes down, the pressure goes up. Again, we're not talking about depth, we're talking about height. So this might be height equals 0, and this would be height equals 1 meter or something, right? We're not talking about depth. So in this scenario, right, what I'm saying is this height is 0. And I don't know the numbers here. I'm bullshitting here. Okay. So let's say this height equals 1 meter, but it could be some other number. And the idea there is we see the speeds are the same. I'll put the pressures right below there. And so we see different pressures for the same amount of speed. In general, right, we could actually do something crazy like this. Whoops. Actually, let's go like this. Let's say I want to make the fluid flow as fast as possible given this scenario. What should I do to make the fluid flow as fast as possible at the output of the pipe? What's one thing I can do to make the fluid flow faster?
Could you make the tube smaller?
Okay. And we see it speeding up. What else could I do?
You could lower the, wait, no, that was change the pressure. Never mind. Let me think.
Could crank up the rate. And then we could see if, again, what we were saying here is if we raise this up and lower this down, we're not really getting any love there, right? Because that associates with the pressure. So the main thing is constrict the pipe or change the flow rate. All right. So that's the main things. Good. All right. So that's fluids in motion. Let's take a look at an example problem where we have to do some paper and pencil, unless there's questions right now. Go ahead and ask questions if you've got them. All right. Let's just go to the next page. It's a fun simulation. Let's pause that so it's not running for forever. Actually, let's look at this simulation first. Imagine I have this water tower here, and I want to let the water flow out. Now I could turn this fluid flow on, and the idea here is we've got ourselves a Bernoulli problem. In this case, maybe I'll use this hose too, right? So I could angle this thing at different angles, and we could analyze the motion of this thing, although it's kind of hard to see that light colored blue against the dark colored blue. Let's see, where are we going here? Straight up versus, let's do, there we go. Okay, I can see, I've got it. All right, sorry that took me so long. So in this case, we could analyze this particular problem if we talk about Bernoulli's equation. In fact, we know pressure at the top plus dynamic pressure at the top plus a gravitational term at the top should equal pressure at the output. I'll say pressure at the bottom. And then we're going to have these other terms, right? One more. Sorry this is taking so long. It's just nice to see it on the screen with an animation. All right, so obviously we could add up the initial quantities. They should equal the final quantities. Energy is conserved for this problem. Now in this particular case, what do you think the pressure is at the top? What do you think this pressure is?
P naught.
That's P naught. What do you think the pressure is right there?
P naught.
P naught. So the idea is it's exposed to air. The pressure is going to be P naught either way. All right. Now, here the water's flowing quite rapidly. I'll call that V bottom. If I stop this thing here, whoops, give me a second. If I turn this thing off, which one's moving faster? Right? V1 is this speed right here, the speed at which this is going down. Which one looks larger to you?
Are they the same?
I think V1.
You think V1 is larger and somebody says it's the same? Let's look at it one more time.
VBot is a little larger.
VBot is a lot larger. Look at it carefully. Right? If I look at it like this, if I angle this, right? We're actually, or think about it this way. This fluid speed is dropping about 1 meter per second, whereas the speed this needs to go, come on. The speed required for this to go way up to this level when it's full, the speed to shoot up that high has got to be large because gravity is pulling it down as it goes upwards. So in this case, wait. Let me just get this set up right. All right. And so the idea is if this fluid is going to top out at the same level, it's got to be going much faster than this. So in practice, think about drinking through a straw, right? As you drink through a straw, you don't see the surface of the cup go down several meters per second. You see it move millimeters per second. Whereas the water at the end of the hose could be shooting out at 1 meter per second, 5 meters per second even. So is everybody okay with that? The fluid coming out the hose is probably moving a lot faster than the water level going down. That's a key assumption that we need to understand. Let's get into it here. This is a variation of that problem, right? Okay, in this case, you guys have already told me some of this information. You said the pressure at the top is atmospheric. The pressure right here is also atmospheric because it's exposed to air, right? Got it. So that's the pressure. That's not the same thing as the stagnation pressure or total pressure, right? Now, clearly there's going to be a V2 here, and there's going to be a V1 up here. V1 is the rate at which this goes down. That's going to be a lot smaller than V2, the flow rate. I just misspoke. The speed as this thing is ejected. V2 is huge. What should be true about the flow rate at the top versus the flow rate down here coming out through the hole?
Would that be equal?
That is equal. Yeah, I love it. I love the desperation. Like, please, can something be equal? Yeah. So we see that area 1, V1, is equal to area 2, V2. Now, remind me here, what's the area of a circle in terms of its diameter?
Pi d over 2 squared, so d squared over 4.
Everybody okay with what I'm writing here? What I'm talking about is I'm saying the fluid in equals fluid out. The speeds might not be the same, but the volume flow rates should be the same. That's what this equation is saying. We're saying rate 1 is equal to rate 2. Okay. Now, I could cancel some junk out, and I could solve for V1. I'm doing part A as we speak. Find the fluid speed, that's V1 at the top. So we're looking for V1. When you solve all this, we get V1 is equal to V2 times what? I think it's D over D squared. Do you buy into that? Hopefully you could see that. Just rearrange, some diameters slip around. Well, look, the diameter of the top of the can is usually much, much bigger. So we're assuming that V1 is now much, much less than V2. Obviously, it depends on the diameter of the hole. If this is 3 inches across and this is 2 inches across, that wouldn't be valid anymore. And in fact, anytime the diameters are in a ratio of about 3 or 4 to 1, that actually ends up being small enough to make the top velocity negligible. Again, as long as the top hole has a diameter of, say, 4 times larger than the hole in the side, we could actually assume this is true, right? More on that why in a second. I'm going to pause. That was part A. So far, so good? Okay. All right. So we're going to assume velocity at the top is now 0 because it's negligible. So I want to determine the speed of the water as it leaves. Let's go to the board. So we know the following. Pressure at the top, P1, plus 1/2 rho V1 squared plus rho G height 1 is equal to pressure at the bottom where the hole is And if we draw this thing, we're saying this entire height is h. We're saying this is V2. We told that this had atmospheric pressure. Up here, we're told that this has atmospheric pressure. So notice in this problem, P1 and P2 both equal P0. We said V1 is approximately equal to 0 because D is much, much greater than little d. That's a lot of assumptions. If I make all these assumptions, what was this height off the ground? This is distance y off the ground. Okay, so this is distance y off the ground. If I look at all this, the pressures are going to drop out. V1 is going to drop out because that's approximately equal to 0. And notice V1 only appears squared, right? So even if V1 is only 10 times less than V2, V1 squared is 100 times smaller. So basically, as soon as this gets a few times smaller, this is completely negligible, even if it really is moving. Okay. It's just such a small term because of that squared. Again, right? So if the diameter is 3 times as big, the speed is 9 times less, which means the dynamic pressure is 81 times less. Negligible. Okay. In this case, what do we get? When I solve for this, let's solve for V2. I'm going to group this down here. I get rho G height 1 minus height 2, moving that to the other side, equals 1/2 rho V2 squared. Rho your density. This works whether you use gasoline, turpentine, Taco Bell hot sauce. Actually, Taco Bell hot sauce is very viscous. We do not want to use that. But notice what I get for V. Our old friend square root of 2GH. Where in this case, the distance is it's the distance between the top of the water and where it comes out. Cool, right? Okay. So now, let's see. Well, that was the first part of this. From here, now that I know this speed, couldn't we calculate the horizontal distance traveled by the fluid? What type of problem is that?
I think kinematics.
Kinematics. We know the speed. We could crank it out. You could make a list, right? What's our list of knowns and crap?
We know V initial, I guess.
Yeah, in the X or the Y?
Yeah, it's X.
That's V2. What else do we know?
You know, A in the X is 0. So VFX is also V2.
What's V initial Y?
0.
What's A V final Y? Something or nothing?
V 0.
It's unknown yet, right? Because it's going to speed up.
And yeah, negative G, yeah. We don't know the time either, so
What about delta Y?
that's Y.
Nope.
Or negative Y.
Yes. Negative y, it goes downwards y, right? So from there, kinematics, trivial. So let's take a look at it. There's all the math. Boring, 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 boring. There it is. Look at that crazy result. Oops, let me make this bigger. That is the result for how far it travels. Now, here's my question. Where should I put the hole so that the water squirts out the farthest? Where should I put the hole to get the maximum value of X?
Close to the bottom.
Why do you think close to the bottom? What's the advantage of that?
Increased height, so the pressure would be higher. Correct.
What's the pressure at the hole?
It's P naught.
So is that what you said accurate?
No.
No. So what advantage do you get when you lower the location of the hole? It's not pressure changes, but
Is it the velocity? No.
yes, the velocity. It's going to be faster, right? You fall. Think about it like this. If I had one water molecule right here, eventually that water molecule, you could imagine it fell this far and then squirted out the side. So the distance you fall, the h minus y, the more h minus y is, the faster your speed is. What if I put the hole right at the bottom? How far is it going to go before it hits the ground?
Just when it just hit the ground.
It would. So it wouldn't fly very far at all. So it can't be all the way at the bottom. Okay. What are the advantages of moving it to the top? Let's say I put the hole up here.
Well, then the speed would definitely go down.
We'd have less speed. But what advantage would you gain?
Less pressure.
You'd still have the same pressure, P naught.
Yeah. Same pressure because it's flow in equals flow out.
You have more height for it to get further.
More height. What is that? If you're higher up to start, what do you also get more of as you fly?
Distance.
More speed.
Time. The higher up you are, the longer you fly. So even though your speed goes down, you're in the air longer. So even if your speed is less, you could fly horizontally farther. Huh. What's your gut say then? How could we figure out the precise height, the precise value of y, which gives the maximum value of x? Oops, sorry. I want the exact value of y that gives me the maximum. I know if I go all the way to the top, it basically dribbles straight down. If I go all the way down to the bottom, it's not going to fly very far, even though it's moving very fast. How do you get the best value of y to maximize x? How do you maximize x, a function?
Do we need calculus for this?
Oh.
Yeah, okay.
H over 2 biscuits. Isn't that cool? And I love to say it, the porridge is just right. So this is what's crazy. If we're running this thing, the optimum, okay, and we're shooting this straight out. Oh, this is complicated though, right? Because this one's up in the air. So let me use a measuring tape here. We're going from this spot, and we want to go out here. So the idea is the lower I go, the faster the water's flowing. But it doesn't quite go as far. Now if I go upwards too much, it's barely flowing out at all. So somewhere in between, right about at the halfway point, should be the maximum. Is that making some sense? This is the ideal compromise between, and so if I mark this out here at the outer edge, we could see if I go to some other height, it should be less than that. Less. And this is making, obviously this is just a computer game, but whatever. All right. What would be different about this problem if I angled it? What would have to change in our approach? Would any of this stuff change? If the hole was angled? What do you think? Go for it.
With the Y chain? No.
This stuff would change. The kinematics part. You'd have a V2 cosine theta and a V2 sine theta, and that's the only difference. Right? Same stuff. Let me ask you something. Let's say I angle this thing straight up. I'm going to angle this thing straight up, and I'm going to play this simulation. How high should the fluid go before it reverses direction, if you had to guess?
The water container's height, where it's at? Yeah, right there.
Let's see, right? Conservation of energy. It was at rest here, it falls down and picks up speed, and then it shoots back up, right? So let's see. Oops. That's the idea, right? Now, obviously, when you angle it, it might not go to that same height because some of the energy is going into lateral motion. Ooh, can we swing this downwards? No? All right, whatever. That gives you an idea. All right. I think that's pretty good on this particular problem. Now, there's a bunch of variations in here. You can see I kind of talk about it. So there we figured that out. Under what circumstances is it okay to say V top equals 0? I went into the details. Let me just show you this. Basically, as long as the upper diameter is about 3.16 times, it's crazy. All right, that's cool. You could do kinematics with these angles. That's great. What if the top is maintained at some pressure other than atmospheric? If it was maintained at some pressure other than atmospheric, these two wouldn't cancel out. You just have pressure. You'd have a delta P in your equation. Same shit, different day. All right. So that's cool. You can handle most of these problems now. If you want to see if you know what you're doing. Here was one. I even talked about going further. What if you had to include the diameter? I wouldn't do that to you on a test. All right. Here's one. I was inspired by a flood I saw in Napomo one day. I was driving by the Vons or the post office, and someone had, I think, driven over a manhole, or not a manhole, a fire hydrant or something, or maybe it just blew. And so there was water squirting up. And so I looked at it and did a quick measurement, and the height was approximately 3 meters. The water was just gushing out. And so this water was shooting up. So I said, let's just do a simulation. Imagine you have a problem. This is like that simulation we just did where there's a pipe and you know the depth of the pipe, you know the size of the nozzles. We know all these different sizes. You could stick this stuff in and figure out It's basically flipping the problem we just did on its head. All right. And now in this case, here, the water is open to air. Here, it is not. So this is a case where you have that delta P involved. And so that is the goal, is figure out how much water pressure you would need to make this ornamental fountain. And then ask yourself, why are we doing ornamental fountains? Just spraying water into the air. And just, I mean, we have enough trouble with water on this planet. Why are we wasting water with ornamental fountains? Just put a piece of plastic there and pretend it's water. All right. Because plastic is so much better for the environment. Oh my gosh. Let me get out of this class. All right. There you go. Ooh, I love this one. This is crazy. A siphon. Yeah. Yeah, right. I just did a quick estimate of the height. Yeah, totally, Jake. All right. So here, a siphon is a really, really weird thing. And let me see if I've got this link. I don't want to waste your time here, but let me see if I've got the link here. Okay, that's the scheduling app. Whoops. I think I have this. This is a good link. I really like this one. Okay. Oh, geez, what's going on here? How do I just say yes?
Advanced, I think, will bring you to the link.
Come on.
Press advanced.
Scroll down
a little
scroll
bit.
down a bit. Yeah.
Oh, sorry.
Yeah,
Hold on.
there's-
Zoom's probably covering something up, huh?
Yeah, it's down below. Just press accept the raise.
There we go. Sorry about that. Couldn't see it all. I've been to this one many times. So this is an article, and you can see that it's legit. Oh my gosh, Zoom, you're killing me right now, Zoom. There's black spots all over my screen, and it's just like killing me. All right. Let me hit Control-Alt-Shift-H. That'll get rid of some of them. So here's the introduction for Bernoulli's equation. And there's a lot of misconceptions about siphons, and I think this clears them all up. So notice they just took some tubing and some 2-liter bottles. And I think this is a good statement right here for siphons, right? So the idea, if you've never used a siphon before, the idea is you fill up a tube with water and you keep one of the reservoirs down below the other one. The idea is, oh, geez. There's going to be a fluid flow here that can carry it up and over the top and down into this one. A lot of people say a siphon is like a chain. That turns out to be a really bad analogy. It just doesn't work for all siphons. It's just inaccurate. So in this case, we see that there's both a gravity and a pressure term. And trying to say which one is driving it. Is it gravity or is it pressure? I like the way they say it. It's not a meaningful question, or it may not be a meaningful question. Surface tension could matter as well. But if we go through all of these things, this is what I really like. This definition of a siphon here at the end. And let me see if I can make this a little bigger. So if you want to know what a siphon is, I think this is the best definition that I have found out there from a physics teacher magazine in 2011. Pipe shaped as an inverted U, we love that U tube, placed between fluids with their surfaces at different heights. It will continuously transfer fluid over the bend from one end to the other through the combined effect of pressure and gravity. It's not just pressure, it's not just gravity. All right. And so if you're curious about this, you could do that problem that I just suggested, 14.30. Let me ask you something. Can you have a siphon work in a vacuum? What's your gut tell you? Maybe those of you that know about siphons or care about them, cool. If you don't, why do you say no?
Well, I don't know too much about vacuums, but I think like the pressure would be constant everywhere in the vacuum, right? So you can't have like a differential in the pressure to cause stuff to move.
But you could have intermolecular forces. And there's a thing called a molecular liquid, and they've done this. And in fact, the original sighting in the 1900s found that you could do this in a vacuum as well. So it's surprising. You would think siphons don't work in a vacuum. Turns out you can make a siphon work in a vacuum with the right types of liquids in the right circumstances. So a molecular liquid, as it's called. So there may be some things you don't know about siphons. And so let me see. I'll see. We're about done for class. Let me see if I could find this. You know what? I'll look for it later. But yeah, you could just Google siphon in a vacuum. So I think it's a molecular fluid is what they called it. You could, yeah. So I don't know where'd that other link go. They may have set it down here. I don't know, whatever. All right.